In this video, we discuss learning outcome number 3 from lesson 6.2, which is all about normal distributions and properties of the standard normal distribution. I'm just introducing you to the concept of a normal distribution, and then we're going to outline the properties of that standard normal distribution. So we've already talked about a uniform distribution. That was one type of continuous probability distribution. Another very important type, arguably the most important type of continuous probability distribution, is a normal distribution. If a continuous random variable has a distribution with a graph that's symmetric and bell-shaped, we'll say that it has a normal distribution. In particular, if the graph looks like that, notice that it's got that bell-shaped curve. It's symmetric about the mean. The values of that continuous random variable would be listed on this horizontal axis. Now, if the probability density function for a continuous random variable is given by this, then we say it has a normal distribution. Now, you will never use this in this class. I just wanted to show you there is actually a function that corresponds to this curve. Every value of that continuous random variable corresponds to a height of that probability density function. Now notice that the probability density function depends on the population mean mu and the population standard deviation sigma. The pi here is a constant from geometry. E is just a constant from calculus. So this is associating a probability per change in x to every x value that continuous random variable may take on. Now, if I want to find the area under the curve, where the curve is given by this function, we'd have to use calculus. Now, we're not actually going to use any calculus in this class. We're just going to use that correspondence between areas and probabilities to find ranges of our continuous random variable, as well as probabilities for a given range of a continuous random variable. And we're going to look up these probabilities and ranges in a table of z-scores. We're not going to use this function at all, but I did want to show you the function because if a continuous random variable has this probability density function, that's what it means for that continuous random variable to be normally distributed. Okay, so we said that. What else do we know about normal distributions? They have a mean of mu. It's going to be represented by mu, and that's right in the center here. It's symmetric. The probability density function, that density curve, is symmetric about mu. They have a standard deviation given by sigma. Just mentioned the symmetry. It's bell-shaped. And the total area under the curve is equal to 1. I put this S in parentheses because I wanted to remind you that there are many normal distributions. They're all described by this function, but lots of different variables are normally distributed. They just have different means and standard deviations. For example, I believe the average IQ score, or the mean IQ score, is 100, and the standard deviation is about 15. For SAT scores, the mean on a particular part of that test, if this hasn't changed, it may have changed since I took the SAT. The mean used to be 500 and the standard deviation was about 100 points. And I believe the maximum score that you could get on something on a particular part of that SAT was 800. So you'd have 500 and then 100 would be the standard deviation from that. So both of those would be described by a probability density function that looks like this. They would just have a different value for the mean and the standard deviation here. But all of the graphs would be exactly the same for all of those normal distributions. You're just going to have a different value down here and different values for those standard deviations about the mean. Now, the standard normal distribution is the subject of lesson 6.1. This is just a special normal distribution. This one has a mean of 0, and the standard deviation is equal to 1. So it looks just like this. Now, if you have the mean in the middle, that's 0, and then you go over here 1 unit and over here 1 unit. Well, remember, the z-score was the number of standard deviations a value was above or below the mean. So if you're listing standard deviations down here, what you're really listing are z-scores. So this is z equals 1. It's 1 standard deviation above the mean. Z equals 2, 2 standard deviations above the mean. Z equals 3, 3 standard deviations above the mean. And then we can be 1 standard deviation below the mean, or 2 standard deviations below the mean, or 3 standard deviations below the mean, or any value in between, or any value from negative infinity to infinity. But we've got our z-scores down here. But again, the z-score is just the number of standard deviations above the mean if that z is positive, or below the mean if z is negative. So with the standard normal distribution, the mean is 0 and the standard deviation is 1. So we've got our z-scores on that horizontal axis, and the total area under the curve is equal to 1. Now, areas under the curve for different ranges of z-scores are going to correspond to probabilities. In the next 2 learning outcomes, we're going to relate those areas and z-scores. So in one of the learning outcomes, we're going to talk about this. If you have a range of z-scores, we're going to try to find the areas or corresponding probabilities. That's learning outcome number 4. And learning outcome number 5, we're going to do it the other way. I will give you areas or probabilities, and we're going to try to find the corresponding z-scores. So that's where we're going. I'll see you in the next video.